I was told you all wanted to see somebody outstanding in their field, so we'll start with that. Thank you. The problem with being videotaped is, of course, now I have to get all new material for the next presentation. I thought coming out west I could absolutely avoid that, since no one, there's only about 12 people out here anyway, and I think you're all here today. Thank you for coming. But I do want to disclaim, of course, since I'm a state employee, any intuition you might have that what I'm going to say is anybody's opinion but my own. Most of what I'll say isn't even my opinion. I'm just saying it because it sounds good. But what you're going to hear is not official policy of anybody within the state police or the laboratories I'm going to talk about or anything like that. You've heard disclaimers before, of course, and some are better than others. Thank you. Essentially, I'm going to take you through forensic science. I'm going to walk you through my laboratory. And at the end of that, we're going to have a slightly interactive session where I'll basically allow you to enter the mind of a forensic scientist and hopefully become one by the time you've left here in a much greater way than you would before we start. We'll go over some case scenarios and kind of decide together what we can and can't do in a forensic setting and try to give you some insight into that process. I will start with who the heck am I, why should you care? We're going to talk about the Massachusetts State Police Crime Laboratory, which through your taxes, unless you're not paying any yet, but we'll get you soon, you pay for the laboratory. We'll talk about individualization of specific kinds of forensic evidence and why they provide such great probative information for solving crimes. And then we'll talk about framing the forensic question. This is kind of my life as a snail, if you were to follow it that way. I went to Indiana University in Bloomington, Indiana, a Big Ten school, thinking that I wanted to be a physician. After the first semester of getting mostly C's, I was disavowed of that thought. But after graduating, I went on to grad school at Northeastern University in Boston. Northeastern used to have a forensic science program for a period of 10 years, and I was the last graduate of that. It actually closed 2 years before I left, which is a true story, and it makes me feel kind of bad. What the forensic science program did is took people who had bachelor's degrees in chemistry, biology, and physics and turned us into little forensic scientists by exposing us to a lot of different kinds of evidence. I had a blast teaching within that program as a teaching assistant and also taking that program in. Essentially, we work with all kinds of physical evidence, and this school was a good way to get a start on that. I did eventually graduate. My father was somewhat surprised. Now, when I was at Indiana, I had a 4-year ROTC scholarship with the Army, so I had to repay that. Before the Army would take me, I graduated in June, and the Army said, you can't come until October. So I, once again shafted. The school closed before I was out. The Army wouldn't take me when I was supposed to go. I went to the Bureau of Alcohol, Tobacco, and Firearms as a postdoctoral chemist and worked on a bunch of bomb and arson-related research. Then I finally did make it to Fort Sam Houston and San Antonio and went through the Army Officer Basic course, learned how to march, learned how to get beat, and then went out to the urine drug testing laboratory at the Forensic Toxicology Drug Testing Lab in Hawaii. I asked for Fort Meade, Maryland, and they gave me Hawaii. Sometimes life is good. I learned that the official vegetables of the Army drug testing system, the urinalysis lab, is leeks and peas. If you have to think about this, we're going to have a tough day today. I also learned that when you're in this business, never ever eat anything with the word whiz in it. So anyway, after leaving the Army drug testing laboratory in Hawaii, I went to National Medical Services from our satellite in space. This is about where it was. What National Medical Services does is it's an independent, private forensic science laboratory. It's the largest one in the country. Essentially, it's an accredited lab, and that means that it meets federal standards. It provides full-service post-mortem toxicology, and it served as the county crime laboratory, and that was my first experience with a crime lab. We had over 120 employees then. They have more than that now. This is a shot of the founder of the laboratory a couple of years before I left in the 90s. Essentially, forensic toxicology uses analytical methods to divine what kind of information there may be in urine, blood, tissues, and homogenates of tissues like brain, kidney, liver, and so forth, to determine if someone might have died as an effect of poisoning or intake of toxins and drugs. I learned a lot at NMS, including hair drug testing. You've all probably heard of urine drug testing. You may have actually been exposed to urine drug testing, hopefully not exposed in a bad way. Your hair actually can serve like a tape recorder of providing historical information of what drugs have been in your body for as long as the hair is on your head. Your hair grows at about 1 centimeter per month. And so as your hair grows out, your hair maintains those months of drug use history or not. And by collecting your hair and segmenting it into pieces, we can tell what your drug use history might have been. if you should shave off the hair on your head because you don't want to, you want to escape detection in this process. I'd remind you have to shave all of the hair on your body off, because we can use virtually any kind of hair. While I was at NMS, I also worked on a number of high-profile cases, including the World Trade Center bombing, the O.J. Simpson case. I was on the defense side, and a case involving a tennis player known as Mats Wilander. He came up positive in the French Open in 1996 for cocaine, and I worked with his defense team in that case. A lot of other cases that we worked on we can't talk about because they were private. I left National Medical Services and took over as the Director of Forensic Services for the New York State Division of Criminal Justice Services in Albany. New York has 25 forensic science laboratories, and I was overseeing the accreditation of those laboratories as well as their federal and state grants, and I implemented the DNA data bank in New York State. Since that time, I've now come to the State Police Crime Laboratory in Sudbury, Massachusetts with the state police. This is the outside of the building. It's a renovated schoolhouse. We moved in 1995. Since you paid for them, these are the $30,000 stainless steel front doors. That's each. And what we did get, we got these great doors. We didn't have a computer network in the walls of the building. But I guess when you're weighing one against the other and you're looking at photo ops, wires don't look as good as doors. Before I tell you about the crime laboratory and the sort of the forensic overlay for the state of Massachusetts, I'd like to kind of take a step backwards on forensic science and give you some idea of why we can do forensic science at all and what it means. Essentially, when you apply science of any kind to a legal inquiry where there's a question that may come up in court, either a civil trial or a criminal case, that could be considered forensic science. We can only do what we do for the most part because of Locard's exchange principle. Essentially, when two objects pass each other closely or contact each other, they're going to transfer trace physical evidence from one to the other. And it's an inadvertent process. As you all sit there today, you're on these Naugahyde seats. They have a certain amount of static electricity to them on a dry day like today. When you leave, you're going to leave behind fibers of your clothing on those chairs. And while you're sitting there, your clothing is, well, you know, certain parts of your clothing are going to pick up the fibers of the person that was there before you. You didn't do it on purpose. You're also shedding hairs while you're here, some of us more than others. As you leave, those hairs will be left behind in a very inadvertent way. None of you are rubbing your heads against the floor. But could I have your shoe? Yeah, this is not a joke. Yeah, thank you. Thank you. It's my size. I always choose somebody about my size. Thank you. Didn't really need it for anything. I just thought it'd be funny to take your shoe. In essence, forensic scientists perform systematic examinations of physical evidence in order to maximize how much information we get while minimizing destruction of evidence and also minimizing, oops, we forgot to do something. We'd like to catch all the evidence that might be available in a scene and store it and use its information to solve crimes and not miss anything. To do that, you really do need to approach things from a systematic manner and use that information that you gather in a very procedurally correct way, following documented standards and hopefully coming up with the right answer at the end. What we do essentially is apply physical, chemical, and biological methods to evidence and try to elicit probative information that helps investigators and death investigators solve crimes. The reason we do it is sort of threefold, and that's on the bottom of the screen. First, we want to characterize something as being important. If you were to kick through the door to come into this building, if the law enforcement agency locally was called to try to investigate the break into this building to steal the equipment that's in the back room, essentially, if you've kicked through the door, the first thing they have to do is to decide, well, is there any evidence of how you got in here? If they should find a footwear impression on the outside of that door, that may be characterized as being important to this case. Now, if routinely people stand on the outside of that door and put their foot up against the door and leave a footwear impression, that footwear impression left behind may not be characterized as being important to this case. So the first thing law enforcement investigators try to do is to determine and narrow down those things on which we have to focus attention. Once we've decided that a footwear impression on this door may be important or characterized as being something we should look into more, we want to identify some possible sources for that footwear impression. This particular sneaker is an Asics sneaker. I would say circa 1983 or so, or you're just a hard man on footwear. In essence, it has a certain size, a certain width, it's got certain aging to it, but on the first day that this was purchased and worn, This footwear impression left behind with a brand new shoe would be equivalent to the footwear impression from anybody else who had the same type of shoe in the same length and width on that day who may have kicked through the door. On any given day, the way our mass production society of our economy works is, especially with clothing and footwear, there's a lot of sneakers just like this out there. Thousands and thousands of them, even with the same size and width. So being able to try to identify where that footwear impression could have come from, we could say it's from this footwear, but on the first day it'd be tough to narrow it down much more than that, saying it's an ASICS sneaker of this type and sole. On the other hand, as you've worn this over time, you start to create identifying criteria on the bottom of this footwear that's going to lend itself to providing identifiable and uniquely individualized patterns on the footwear impression you leave behind. It has a lot to do with how much you weigh, how it's distributed on your body, where you walked, how you walked, and so forth. So this footwear now has quite a bit of individualizable characteristics. The point being, of course, don't kick down the door, or if you do, make sure that someone else is wearing your shoes at the time. Thank you. Those types of evidence that provide individualizable characteristics are often the most important for solving a crime or providing the most probative information. Latent fingerprints, you all know that your fingerprints are different from one another. In a gross sense, they're categorizable into large categories of loops, arches, and whorls. But after that, it's the unique indentations within those patterns that give us individualizable characteristics. Your bite marks can be characterized as being unique to your body. Your teeth form differently than everybody else's. How you bite with either an overbite or an underbite. The way that you apply pressure with your mouth are all different among each other. And so bite marks can be characterized back to the individual who bit, or to their teeth, and then you have to explain where your teeth were that day. Footwear leaves behind a unique impression, so do tire impressions. Not on the first day they're sold, but after that as they start to develop wear characteristics. Firearms and tool marks leave behind individualizable characteristics, as do blood and bodies. Now for latent fingerprints, whether you're developing with a powder method, the old-fashioned way where you're using contrasting powders, or you're using super glue fuming on non-porous surfaces like plastic Coke bottles, the fumes in this case will envelop the bottle and essentially stick to those areas where there's protein left behind in the fingerprint ridge detail, and we will sort of get contrast of super glue fumes sticking to fingerprints and not to the rest of the bottle in great measure. We can use ninhydrin protein stains on porous surfaces like cardboard or paper, and the fingerprint now that we couldn't see with our naked eye becomes visible with this ninhydrin purple stain. No matter which way we develop it, the point is to get the latent fingerprint. Once we have that latent fingerprint, we then can start to look at not only the gross pattern, in this case a loop pattern. You can see that's kind of in this area here. You have a loop. But the individual points of comparison of where a ridge might bifurcate or end, where there might be an island or a dot, those are the points of comparison that allow for individualization of the fingerprint. We compare these latent prints to rolled, inked impressions of fingers from people who have been arrested, gone into the military, maybe part of some other government service where their fingerprints were collected. And one of the things to remember is if you're a fingerprint examiner and we find fingerprints at someone's home where there was a break-in or a sexual assault or a murder, how do we figure out whose fingerprint it is? Well, the first thing you do if you're in a home is get elimination prints from the family. Make sure it's not someone who lives there. Or if it is, try to ascertain whether or not the prints where they're residing on the surface should have been there from that person. Okay? But in reality, it's very hard to remember inked impressions in your head as an examiner. So you're left with this latent impression. You want to compare it to known impressions that are close to that and sort of narrow down your search as much as possible. We have a computer that allows us to capture fingerprint information and store it in a digital form, and then allows us to compare latent impressions against that data bank and provides a number of characteristic fingerprints that might match the one that's an unknown at a crime scene. This system is known as the Automated Fingerprint Identification System, or AFIS, and it provides a computerized database of stored fingerprints, historically important ones, either in criminal senses or as known prints from rolled impressions of military members and others, and allows us to compare these. The way it basically works is you have what looks like a photocopier machine. The white card with the fingerprints rolls into the machine. a digital image is made, and an algorithm takes this and stores it in a digital format inside of large computer banks. In 1986, we had the third APHIS unit in the country. Today, we still have the third APHIS unit in the country. We haven't changed our technology since then. Each one of these massively parallel processing units has the power, the computing power of 1/8 of my laptop. So it's kind of old. And the mass storage devices behind that in the background have the storage capacity of 2 floppy disks. So an $8 million bond was let a couple of years ago to transition APHIS into the future. And essentially, that APHIS transition should be done by November. It's going to bring a lot more power to the process of this comparison of fingerprints and should provide much better investigative utility. Hopefully, you'll never see this for real. This is what it looks like just before you're shot to death. I lost the cameraman after this. I don't know, he ran away. But in any case, firearms evidence also provides for unique individualization when involved in a crime. There's a couple of things that the firearms unit does at the state police laboratories. The first of those is if you're accused of a crime in which a firearm was used, you're going to be accused of using a deadly weapon. We have to show that the thing in your hand at the time or that was recovered from you is in fact operable. So we test fire the weapon into a water tank or into a snail trap, a long cylindrical trap the bullets fall out of, in order to recover the bullet and also to demonstrate that the weapon operates. Once you've shown it operates, you may want to do some comparison between slugs removed from the head of a murder victim and the gun test fired in the laboratory in this case. Now, this water tank is essentially a stainless steel tank. It has water circulating through it. It's chlorinated. You could actually swim in there, except for about 3 times a day it gets a little dangerous. But other than that, you could swim if you were small. We essentially also have a library of weapons, both shoulder-fired weapons and handguns. This does 2 things for us. Many times, someone who doesn't want the weapon they used in a crime to be recovered may throw the weapon away, but before they do, they may try to destroy its mechanism. They may remove the firing pin, they may take the springs out, they may do other things to it to make it so it's difficult to determine what it was used for or if it's even operable. We can take pieces off of a weapon in the library and rebuild the weapon that was recovered from a suspect or from a riverbed where it was dumped, and then test fire that weapon. Now, as long as we remember that what we're essentially trying to do with bullets is to get the characteristics of the rifled barrel of that weapon impressed onto a bullet lead, recover that bullet from the tank and do the microscopy on it, it doesn't really matter what other components of the guns we might switch out. On the other hand, if we're looking at firing pin impressions and we've had to replace the firing pin on a weapon recovered from a riverbed, that's not sensical. So we use this library of weapons, if you will, to rebuild destroyed weapons. In addition to that, if someone tells us that their crime was committed with a certain type of weapon, you can kind of lay out a lineup of weapons and say, well, what kind of chrome barreled weapon did it look like? Was it like this? Was it like this? Was it like this? Kind of like mugshots. The unique individual microscopically discernible features of firearms evidence come on both sides of a cartridge case. The bullet side is shown here. In essence, you can think that barrels of the weapon are about this big around. Bullets are about this big around. They're fatter, but they're softer than the barrel of the weapon. Weapon barrels are made of machined high-carbon steel, essentially very hard metal. Like a football, if you were to take a football and try to throw it through the air with no spin, the ball won't go very far and it won't be very accurate. On the other hand, if you throw a spiral, the football will go more accurately and a longer distance. We do the same thing with bullets. Essentially, if you throw a deer slug out of a non-rifled barrel, like a shotgun barrel, it'll just kind of flutter through the air. It doesn't go very accurately or very far. But as soon as you start to impart spin on a slug, it will go much more accurately. Rifle barrels have machining in them a groove like this. They can have anywhere from 4 to 6 to 8 grooves, depending on what type of firearm it is. So as you take the big fat bullet and push it down the barrel, it's going to be grabbed by those grooves and spun and made to spiral, and that's why it becomes more accurate. Now, the trick with tool marks, and rifle barrels really provide tool marks, for that barrel to be machined with these rifling, we had to do a mechanical process. All mechanical processes provide unique, differentiable microscopic characteristics to the metal that's formed. In essence, every time you put tools to a hard metal tool to a softer metal, you're going to leave behind microscopic imperfections. And those now are going to be impressed on the bullet as it passes down the barrel. On the other side of the cartridge case, if we're pushing the bullet out of the gun this way, there's an equal amount of force pushing back on the cartridge case from which that bullet came this way. So essentially, as a firing pin impresses itself into the back of a cartridge case and causes the burning process of powder inside that cartridge to start the bullet that way, the cartridge case gets pushed backwards. There's a hard metal surface behind it called the breech face. It's machined, and so it has imperfections. And those imperfections are pressed against the back of that cartridge case, and that's where the characteristic unique identifiers come from on the cartridge case. In the ballistics laboratory of the state police labs, essentially we're going to mount the unknown on one side of a double microscope and the known on the other side. Then using an optical bridge, you can actually look at just one side or just the other side, or you can overlay them microscopically and visually and compare the individual characteristics left behind. Like the fingerprint, where the gross morphology of that fingerprint was a loop, but the unique characteristics were where all the little ridge endings were and the bifurcations. The same is true here. The width of the impression of that groove of the weapon left behind from the rifling process is characteristic of Smith & Wesson versus a Glock versus another type of firearm. On the other hand, it's those unique individualizable characteristics left behind inside of that impression that provides us with the unique individualization. These little lines here, these microscopic characteristics, are what tells us that this bullet recovered from the head of a murder victim came from the same barrel as the bullet that was test fired in the lab. It's not very hard when you get to this point. Getting to this point is often tricky. Just like with AFIS, where we can collect information for fingerprints and digitize it, we can digitize firearms evidence as well. This is the unit that does that. The little red thing underneath the microscope there is essentially a plastic pin on which we've mounted a cartridge case. We can view down on the back of the cartridge case and get those firing pin impressions and the breech face marks, digitize them, and store them as digital images. There's an algorithm that turns the digital image into a little mapped word, and the word represents that cartridge case. We store that in the computerized dictionary of bullet cartridge cases, and then if you get an unknown from a crime scene, we can recover it, image it, and use the stored images against it to see which one of those weapons in our library it might have come from. We kind of like semi-automatic weapons. In the old days, revolvers, you had 6 or 8 bullets in a chamber, and the chamber essentially rotated with each shot, but you took the cartridge cases with you. Semi-automatics are much better. You go poom, plink, poom, plink, poom, plink, and if you don't pick them up, you just leave behind the cartridge cases, we get them. We can view them, computerize them, digitize them, put them inside them, and do comparisons later. It's kind of nice. This system is known as NIBIN, the National Integrated Ballistics Information Network. It's also a palindrome, which people in the city don't understand what that word means, but I know you do. This used to be known as DrugFire. There actually are 2 competing systems, one from the Bureau of Alcohol, Tobacco, and Firearms, the other one from the FBI. It might not surprise you that they don't talk to each other. Those machines are mutually exclusive data sets. NIBIN attempts to harmonize the data. It doesn't work perfectly that way yet, but it might in the future. Essentially, it's used to link serial shootings together so we can help solve them. In Massachusetts, the state police has NIBIN, and we have already loaded in over 750 cartridge cases and bullets, and what is cartridge cases from evidence and test fires. We have 1 workstation now. We're getting another one later this year. We've already had 6 cold hits, 6 cases that were linked together using this computer. That's something that couldn't have been done without this NIBIN system. Within the laboratory, I'm going to talk about DNA, but first I'm going to talk about criminalistics. You can't do DNA until you do criminalistics. Essentially, I have chemists who are hired by the state police. Part of their duties are to go to crime scenes. So if local law enforcement in Greenfield gets a 911 call and they go, uh-oh, something's happened bad in this house. Local law enforcement rushes out there, they look in the window, and there's blood everywhere. Before they go in, they may go in and check and see if anybody's alive or needs medical attention. If someone's dead, they're probably going to creep back out and make a quick phone call to the district attorney's office, who has a physically co-located state police detective unit, who may place a call to the Crime Scene Services Unit, also made up of state police troopers who have specialized investigative skills, who may also place the call to the crime lab. The crime laboratory will send out a chemist. So at your scene, you now have local law enforcement, state police detective unit, someone from the district attorney's office, one of the assistant DAs, someone from the Crime Scene Services Unit in Agawam, probably for here, or yeah, probably Agawam, and someone from the crime laboratory, probably from the Agawam lab as well. All of that's designed to get the right expertise at a crime scene, to gather small trace evidence from crime scene evidence, leave behind the car, the house, the bedding, whatever you have you, and take the trace materials with us. Make sure we document the patterns that are left behind, because that may be very important. Not just that there's blood and it's from the victim, but what was the shape of that blood? What did it mean about how the blood got there? We also try to identify at the scene, if there's a red-brown stain, doesn't mean it's blood. Ketchup looks kind of like blood when it's dry, as does rust and a number of other materials. We can do presumptive tests at the scene to tell you this is a red-brown stain that is blood versus this is rust from underneath the car. Within the crime laboratory, once evidence gets back to us, one of the things we try to do is to lay clothing and bedding out and try to determine the presence or absence of trace materials like hairs, fibers, glass, paint, soil, phytons from soil. If there's different stains available from biological sources like semen, saliva, urine, feces, and blood, we try to identify those on the material. We try to characterize what the shape of the stain is, and then we recover that. We can cut out the stain, or we can leave it on there and take a small portion of it. We also use high-intensity ultraviolet light sources that make things fluoresce in the dark or draw the light in. Blood, for example, under high-intensity ultraviolet light tends to look dark on a bright background. On the other hand, seminal residue glows a bright whitish blue under these UV lights, and it's very easy to find. Even if there's just a little tiny speck of it, we can find it. In addition to that, we get weapons within the criminalistics lab. When you shake someone's hand, I'll do this here, thank you, nice 5-second handshake, we've just transferred about 5 nanograms of DNA. We can test for 0.5 nanograms of DNA. So every time you touch somebody, if you ever meet Elvis, obviously, shake his hand a lot, get a big sweaty handshake with the guy going, come home and swab yourself. Now you got Elvis on a stick. But I know he's dead, I know. But maybe he's not. And there's aliens. In any case, even on a weapon where you can't see blood, we may be able to recover blood or other bodily fluids and tissues and the DNA that's contained within them. It doesn't take much is sort of the point. We also process reported sexual assault kits. If there's been a victim of a rape or a sexual assault and a kit is collected in a controlled emergency room setting, those kits come to the laboratory and we can recover things that are swabbed from the patient, combings from the patient, and so forth. We again start with presumptive tests and conclude with confirmatory tests and may do DNA. But the criminalistics unit has to do its thing before DNA can do its thing, okay? Many things that criminalists do only involve our eyes. The simple characterization of trace materials generally starts with macroscopic and microscopic views. It's very easy, for example, to differentiate wool fibers from man-made fibers like nylon. You can do it too. It doesn't take much training to do that. The trick is remembering that there are over 66 varieties of nylon that are used in various materials. We want to differentiate not only that it's nylon and characterize its polymeric backbone, but also show where it came from. In the OJ case, finding a nylon fiber was not as important as knowing that that nylon fiber came from a specific kind of carpeting only used in Ford Broncos during a 2-year period. Doesn't matter so much that it's nylon. That's important first, but then where did it come from? Narrowing the possible sources from a class characteristic to an individual characteristic of it's that truck. Well, you can't quite do that in the OJ case, but you can get pretty darn close. It's that truck or all the Ford Broncos made between 1983 and 1984. Well, he happened to be driving one of those trucks. But I'm sure it wasn't OJ. Serological evidence, the big 3 for us as far as what's useful for recovering DNA are blood, semen, and saliva. They generally contain large enough amounts of nuclear DNA to provide for individualization. And usually that's what you think of when you watch the Discovery Channel, the New Forensic Detectives, and all these other shows you watch. DNA identifies the bad guy. DNA shows the victim was in the trunk. DNA, 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 identifies, identifies, identifies. There's more to it than that, though. Again, what is the physical presence or position of that stain? If we find the victim's blood next to the victim where there's been a shooting in someone's kitchen, well, duh. The victim's dead and there's a pool of blood. We don't need to characterize the DNA of that pool. On the other hand, or if we find human blood in your bathroom, does it matter? No, if you shave, you probably cut yourself from time to time. If you have a nosebleed, if you cut yourself in your hand, you're cleaning up, you're going to find human blood. On the other hand, if you find human blood where there shouldn't be any, or if you're a vegetarian, you find chicken blood in someone's kitchen, that could be a bad thing too. But in any case, where is the stain? What's its condition? Is it a brand new scene and yet this looks like a crusty old stain? That can tell us something about whether we should do the testing. What directionality does it show? When you get hit with a baseball bat, the blood is basically going to follow the direction of force, but there will be some bounce back. The very first blow, if I take the bat to you and hit you first, you don't have anything on the outside of your head yet except your hair and your skin. So the first blow may cause you to start bleeding, but you won't get any blood pattern behind you from that. On the other hand, another blow now, if you started to bleed, is going to hit that blood and disperse it behind you and to the side. But it won't push much in this direction where the blow is coming from. A little bit, but not much. That kind of directionality and pattern behind you on walls or underneath you can show us what kind of activity were going into that distribution of blood. And obviously, or it may not be obvious, but the more force that you use when you're causing someone to bleed, the greater the likelihood that you'll get smaller and smaller drops. If you're merely standing here and your hand is at your side, if your finger is bleeding, you're going to be dropping blood on the floor with low velocity. And you're basically going to get nice round droplets because the angle is 90 degrees and there's not much velocity forcing the blood to go downwards. It's just dripping out of you normally. If you have an arterial spurt going on, now you've got some directionality going. Let's say they cut my carotid artery, it's going to be going. It doesn't really sound like that, but just for effect. But it'll be sort of discharging in a direction, and now when it hits the wall, we'll be able to get some directionality from that. If I hit you with a baseball bat, I should start to see medium velocity droplets left, which are smaller and smaller in shape. We're starting to break the liquid blood up into smaller and smaller droplets. If I shoot you, I may end up with a mist of blood behind you because there's a lot of velocity, a lot of energy going into your body, and it's dispersing that blood. Now, some reconstructions are easier than others. This is a pretty straightforward one. You usually think, though, of information content when you think of DNA. In the old days, serology was used. And the old days in Massachusetts was, up till September of 1998. We didn't do DNA testing in the Commonwealth until May of this year. All the DNA that was done in the Commonwealth was sent out to private laboratories. It continues to be sent out to private laboratories during the period where we're going from not doing DNA at all to doing the full complement of DNA that's needed by the state. But part of the reason that I came to the state was to try to help accomplish that goal. We have now opened the DNA laboratory. It's a wonderful thing. We can't do all the cases we want to do. We don't have full staffing yet, but we're getting there. When we did serology, we could sort of show the ABO blood type, we could show PGM markers and other blood serology characteristics that would allow us to say, well, the blood that was found on the crime scene floor is either from the victim or it's from someone pulled randomly from the population with a probability of like 1 in 10,000 or so. Now, district attorneys at the time thought that was great. We've eliminated 9,999 people as being the source of that blood other than the victim. And there's only 6.5 million people in the state, so that's a pretty small group who could have left the blood stain. That was really good. That led to a lot of convictions. Then DNA was invented. A guy in England invented restriction fragment length polymorphism, RFLP. That's one of those word wealth things, got a lot of letters in it. Anyway, you can use it on your friends at parties. They won't have any idea what you're talking about. And if they're drunk, they'll think you're very clever. Maybe if you're not drunk. This is a school with no alcohol, I'm aware, so you have to go off campus. This message brought to you by the Director of Public Safety for the school. In any case, what RFLP offered was high selectivity. Instead of saying that the random match probability when we had a comparison that matched for RFLP was 1 in 10,000, RFLP gave us 1 in a million kinds of characteristics of having random match probabilities. You've probably seen RFLP kinds of data on television before, and in the OJ case. This looks like sheets of X-ray paper on which there's fuzzy dots, and if the fuzzy dots compare like a barcode, then it's the guy's blood. Okay? 1 in a million, it's as good as an identification. Right? Right. Juries love RFLP. Big numbers, I can do that with my own eye, that kind of stuff. Well, when it's not really a clear fuzzy dot, it can be difficult to interpret, but for the most part, it was pretty straightforward. The problem with RFLP was it took about a dime-sized drop of blood to do it. It took like 50 spermatozoa heads. That's a lot of sample. We may not have that much sample left behind in the crime. So because of that, if you give scientists a problem, we'll develop technology to solve the problem. It'll cost a fortune. That's what we do for a living. So PCR, or the polymerase chain reaction, was invented. Now RFLP was invented by Alec Jeffreys in the United Kingdom, a very smart guy, university setting. He ended up being knighted. He's now Sir, he's Sir Alec Jeffreys. PCR was invented in America by an LSD dropping surfer dude in California. Aren't we America? It's a typical Brits versus the Yanks. But in any case, PCR, what it does is it allows us to take a very small amount of DNA and essentially like photocopy it or amplify it, and therefore end up with enough copies that we can then do the characterization of identity. The problem with PCR in and of itself is the kind of PCR we were doing in the beginning gave great sensitivity. You could do it on a little micro drop of blood left behind on the watch of the person that shot the guy. But the selectivity was back down to that 1 in 10,000 to 1 in 100,000 kind of random match probability. Not as exciting to a DA who has now become used to RFLP testing, where you get 1 in a million. Well, you got a problem? Ask scientists. We develop technology. We spend your money. That's what we do for a living. So along came short tandem repeat testing, STRs. STRs is how our laboratory is now in business, and the Boston Police Department Crime Laboratory as well. It is essentially the state of the science in forensic DNA testing today. What it does is it takes the polymerase chain reaction, where we amplify small amounts of DNA, yet characterizes more points of comparison, kind of like RFLP. The way this works essentially is the little stain that came over across the hallway in my laboratory from the criminalistics unit, where we took a little 2 by 2 millimeter cutting of the blood stain from the victim's shirt that we think may have come from the suspect because he was cut during the stabbing. That little piece comes across in a little plastic tube, the little green tube in her left hand. She's going to extract the DNA from that little piece of cloth. The extracted DNA goes into a thermocycler, which provides for the polymerase chain reaction amplification of the small amount of DNA, and then we characterize and separate the fragments of DNA that we've now amplified in what's known as a capillary electrophoresis instrument. 80,000 bucks a piece. We got 3 of them. We're getting another one this year. Thank you very, very much. The good news is we're doing things more expensive today than we ever have before. I know. Things cost money, but if you want it done right, this is the state of the science. After this instrument is done separating big groups of DNA into the individual components, it goes through a computer system to make sure that we've got good quality control on the batch of samples that got tested, and then we print out your profile. Now we're going to look at 13 unique points of comparison on your DNA molecule. The way this works is, essentially, each one of these groups of peaks represents 1 point of comparison for your DNA. One group, another group, another group. We're going to do 13 of them. Wow, I must have really been bad. Thank you for coming. Your check, I'll still send the check. Thanks for coming. Yeah. The way this works is that each one of these points of comparison, your parents gave you one characteristic from each of them. For example, if your mother had the profile at the FGA point of comparison, or locus, she would end up with 2 little peaks, a peak there and a peak there, for example, if she had the 18, 19 characteristics at this point of comparison. If your father had the characteristics of 29 and 30, he would only have these 2 little peaks. If you are their child, and again, that's a big if, I know, we're out west, but if you are their child, you have to be, if your mother's an 18-19 and your father's a 29-30, all you can be is an 18-29, 19-30, 19-30, or I've got it messed up in my permutations. 18-29, 18-30, 19-29, or 19-30. That's all you can be if you are their child. Okay? Reading these is relatively straightforward. It's not like the old days where you had these barcode looking things with little fuzzy dots and you tried to read them. You either got a peek or you don't got a peek. When there's a unique blood source, if there's a mixture, it's a little more complicated. But the point here is, though, at each one of these points of comparison, we're going to look for those characteristics of you. You may share those two peaks with up to 10% of the population at each one of these points of comparison. For example, if you may have a characteristics of 1830 at the FGA point of comparison, and 10% of the population may also share that. On the other hand, this may have only 4% sharing of your profile within the general population. This one may only have 2%. But when you multiply 0.1 times 0.04 times 0.02, and you keep doing that in the other points of comparison along the way, 0.02, 0.1, 0.03, the statistics get very big indeed. For example, the blue dress. Here's the blue dress, okay? At first, I never touched that girl, right? Okay, well, didn't know the blue dress existed. As soon as the blue dress existed, well, maybe I touched the girl. Well, DNA STR profiling was done on a seminal fluid stain that was recovered from the blue dress. That stain either came from Bill Clinton or someone pulled randomly from the population with a probability of 760 billion. So, it's Bill. There's no argument about that. The identity of that stain is from the president. There's still a criminalistics aspect, though. What are the circumstances of this incident? If it's vaginal intercourse, this may be a drainage stain. It may be somewhere low on the dress. Where was the stain? High on the dress. It corroborates the story of consensual oral sex. So, in any case, that's essentially the kind of numbers you can get. In our own laboratory, the very first case we've reported from our DNA laboratory involved a blood stain on the sweater of a suspect involved in a non-fatal stabbing. The victim's blood was thought to be on the sweater of the suspect. So we tested the victim's blood, the suspect's blood, and the blood stain on the sweater of the suspect. It turns out that the victim's blood and the blood stain on the sweater matched in every point of comparison on these 13 points of comparison under STR testing. So it was either, and the way the statistics came out, it was either the suspect either had the victim's blood in his sweater or the blood from someone pulled randomly from the population with a probability of 1 in 820 quintillion. So it's the victim's blood on the suspect's sweater. Identity is formed. It's a very powerful tool. In that particular case, that led to a plea and 25 years in prison. No trial, no expense. It's very powerful. When done correctly with good quality assurance, it should lead routinely to us not having to go to trial. Trials are almost the most expensive part of most cases. One other thing we can do in the far left to your eye, we can look for the XY chromosome using this test as well. So we can tell the difference between male and female and mixture kinds of samples. That can be very powerful when investigating rapes and sexual assaults. One of the tools we use for comparing our data with others is a computerized tool, and that requires us to have some standards that everybody adheres to, using standardized methods to create database and link our laboratories. Now, not everything can be standardized perfectly. The world doesn't allow for that. On the other hand, you can make things look pretty much alike and allow us to share our harmonized data. Now, one thing to remember is that in all laboratories, you sort of have this situation. Okay? In a modern DNA laboratory that meets federal standards, you have local quality control. Our laboratory does that on a daily basis. Every batch of sample has known positives and negatives. In addition to that, I have a quality assurance program that overlays my entire laboratory. Make sure that people are trained and competency tested. They do proficiency tests. We've monitored their testimony. We make sure that in an ongoing way they're getting continuing education to develop as professionals. On top of that, you have a federal overlay of national standards. All of those together should make you sleep at night. If you are implicated in a crime and you left behind your DNA sample, rest assured, if we find you as a known and can compare you to that unknown, any finding we make in our laboratory is likely to be quite forensically defensible. That's the bad news if you're a bad guy. Good news if you're a good guy. The framework for comparing data in the United States among DNA laboratories is known as CODIS, the Combined DNA Index System. The way it works is essentially at the local system, we have a local DNA index system, or LDIS. I can store the profiles of semen stains found in various kinds of rapes in our jurisdiction. And even if I don't know who the perpetrator is, I can show that these cases are linked to one another and help the investigators talk to each other and try to figure out what commonality there is among suspects, MOs, and so forth. But if I want to compare with Boston, I can't do it automatically without uploading my data excuse me, to the state DNA index system. Now, the state DNA index system is in my lab. It's in a different server, but it's in my laboratory. We can thereby compare our data with Boston. If I want to compare with California, Florida, Virginia, Maine, New Hampshire, Vermont, Connecticut, I have to upload to the National DNA Index System in West Virginia. They put it in West Virginia because there's only 4 DNA profiles. It seemed easy. I could have said Western Mass, but I didn't. Excuse me. There are 4 types of data inside the data bank. What I've talked about so far are casework samples. I find a blood stain, I characterize its origin using the profile, and I store that profile. Excuse me. I can also store the profiles from convicted violent and sexual offenders. The law allows us to do that, and I'll tell you about the law. We also can store profiles from missing persons. If someone's body is recovered in the Berkshires, we can take DNA from it, profile it, and store it in our computer. And if later parents come forward and say, you know, that might have been our son or daughter out there, we can take their DNA profile and see if the one in the databank matches it. Essentially, what the databank is trying to do is to link cases to offenders or cases to one another. If we can do that, we provide investigative leads, and those can lead to solving the crime. In essence, it's best used for linking serial rapes and violent crimes. It helps us, though, not solve the crime so much as get another sample that helps us solve the crime. The way it works is when I get a linkage between a convicted offender and a crime scene stain, that is used in court to get another blood sample from the convicted offender. I profile that, and if it matches the crime scene stain, that's used against that person in court. Okay? So our data bank is an investigative tool, not a prosecutorial tool. Our state was the 47th state to have a DNA data bank law. We were the first and only state to have ever been enjoined by the ACLU against using the data bank law. There have been 3 injunctions. The first of those involved the fact that when blood started to be collected under the law, we had not promulgated rules and regulations on how the collection would be done. So rulemaking was done, and that injunction was lifted. The second injunction involved essentially the Fourth Amendment rights of people who were involved as convicted offenders. The way the court worked is it said, or the single judge who put the injunction in place said, you know, if there's not reasonable suspicion to think that guy did that crime, we shouldn't have his blood. You have a Fourth Amendment entitlement to be free from unreasonable search and seizure. The judge said, I think that's what's going on here. It's unreasonable. The databank law works on the fact that recidivism is a reality for violent and sexual offenses. Those that have raped before and been sentenced and convicted for rape are far more likely to rape again than someone who's never raped before. That's the notion of recidivism. It has large scientific basis, and it is the foundation of data banking laws. The Supreme Judicial Court in April dissolved this particular injunction, and the Superior Court liberated it in May. The third injunction involved a person in the Department of Correction facility who said, I'm not in prison right now for one of these 33 specific offenses that you can get my blood for. I'm in for auto theft. I had an aggravated rape before, but I've already done my time for that. The point of recidivism, though, is you're going to do it again someday, more likely than someone who's never done that crime, never been sentenced, never been convicted. Once again, the Supreme Judicial Court dissolved that injunction for us at the Superior Court level in August. It's a very exciting world for DNA right now. I think it brings a lot of powerful investigative assistance, but it is only assistance. And I'll remind you again, the DNA does not solve the crime. Criminalists help investigators solve these crimes. We're only part of the team. Now, you've probably heard enough about OJ in your life, but I'll tell you just a little bit more about it. Whether you liked OJ number 1 or OJ number 2 is somewhat immaterial. It taught us a bunch of lessons within the forensic world. One of those things it taught us is this is not necessarily always a justice system. It is a legal system. Sometimes it works as a justice system. Sometimes it doesn't look like justice when we get done. But that's not because of science. It's not really even because of lawyers. It's because that's how the process is designed. It's a pendulum in essence. Sometimes the pendulum swings a little far from what we think is centered. That can happen. Regardless of your opinion of O.J., it very much pointed out this fact. Another thing it pointed out is never wear ties with blue jeans. It looks silly. But anyway, Barry's a good friend. I'm sure he wouldn't be mad if I showed his picture. He likes his picture being in the paper. But one thing it did for forensic scientists specifically was it taught us that helping investigators frame the forensic question can be very important for helping get that crime solved. Chemists and other more highly trained investigative people who provide investigative assistance should be part of the initial team of investigators that try to solve crimes. The accreditation of laboratories is important. The labs that were involved in that case were not accredited. It would be nice if they were. One of them now is, and the other one is about to be. We really should prepare witnesses before trial, not during the trial. It's always better to know what they're going to say before you ask them. Most lawyers will tell you that's a proper approach. And it's nice to have broadly trained scientists. If all you know how to do is DNA, you may miss some trace evidence, hairs and fibers, glass, paint, and soil. If all you know how to do is weapons, you may miss what's left behind for other types of evidence. So it's important to broadly train people. How much time do I have left, since you've already flashed me a 10-minute sign?
4 minutes.
Say again. 4 minutes. Okay, we're going to do one case together. If we have time for another one, we'll do it. Essentially, I'm going to take you through the thinking and framing a question. All of these are real, and we'll get to as many as we can in the time provided. Cartridge cases are found at the scene of a double homicide. I get a phone call from an investigator who says, "We found these cartridge cases. Can you check them for DNA and fingerprints?" The thinking is that the guy who loaded the weapon grabbed the cartridge case and loaded the weapon, and his fingerprints and DNA will be on there. Because I told him, you know, when you shake hands, you transfer all this DNA, so there must be some DNA on the cartridge case. The easy answer is, you bet we can do that. The questions that come up first, though, are should we? And what do you want to know about that decision? How do you frame the question for him? Can I do it? You bet. But let's consider some things. Where did we find those cartridge cases? Do they have anything to do with this crime? I don't know. Where'd you find them 100 yards away? Have you been in most city streets, say Springfield or Chicopee or Holyoke? There's cartridge cases all over the place. You know, accidental firings, I'm sure. How were they collected? Did someone pick them up for us? If they did, whose DNA and fingerprints do you think we'd find even if we could? What is the temporal relevance? Were those cartridge cases at the right place but had nothing to do with this crime? What's the effect of discharge? If we discharge a weapon, what happens to fingerprints and DNA? Has anybody ever studied that? No, not a lot. How are we going to compare these to anybody if we don't have them in a database? What are you going to compare the DNA to? Are they a convicted offender, do you think? Have any suspects? What kind of weapon is it? You find a slug in the head of someone who was shot. Is it the right cartridge case for that kind of slug? If you find a 38 slug in their head and a 22 cartridge in the street, why are we doing this test? Okay? We're going to make some assumptions also. The person that loaded the weapon is the person that shot the weapon or had something to do with the crime. If this is a stolen weapon and it was loaded by the owner, but the owner had nothing to do with this crime, it may not help us. And again, we don't know if DNA and fingerprints are going to survive this process. So, get the feeling? Okay, now how much time do I have left? 2 minutes. Okay. The bottom line is, whenever we're doing this, this is what it looks like for what we'd like. This is the information we desire. The reality is, this is the information we get. So, as a forensic scientist, what differentiates us often from people who do EPA kinds of testing, clinical laboratory testing, and other kinds of applications of analytical science to problems, we have to think and fill in the blanks without trying to say, this is the answer, let's prove it with science. We actually have to keep our mind open and use analyses as best we can to develop as much information as we can.